I'm Severin. I'm a second year bioinformatics and systems bio PhD student working with Dr. Benjamin Smar. And this project, which the title has changed a little bit since its inception, is Matlab integration onto the National Research Platform for faster, more reliable time frequency analysis. Oh, whoops. Sorry, I think it's, okay, there we go. Cool. So let me dive right into the overall goal of this project, which was to integrate Matlab onto the National Research Platform. And I'll explain what that is in a moment, and more specifically to integrate Matlab into our existing Python-based workflows. So at a high level, this project was the results of some, or rather prompted by the results of some not so great results we got from Python-based frequency analysis packages, both in terms of actual results, runtime, and memory usage and management issues, as we are dealing with quite a bit of data in our projects. And we wanted to look into Matlab as an alternative to Python for more efficient and quite possibly more correct time frequency analysis. So just about the National Research Platform, or the NRP. Our lab does almost all of our work on the NRP, and the NRP is this all-in-one system of computing resources, research and education tools, and more, and whose primary computation, storage, and network resource is this pretty big, approximately 300 node distributed cluster called Nautilus. And Nautilus has over 10,000 cores and 1,000 GPUs, I believe, distributed across the US. And this image here just shows just the distribution of GPUs across the US. And I believe more have been added since fall 2022. And for us, it's this amazing and I believe free, I want to say, resource that lets us request compute, RAM, and GPUs. And there are various Docker images you can choose from to launch various server environments that are appropriate for whatever you're doing, whether it's just day-to-day coding or you need to train some kind of a deep learning model. Most images on here are Python or R-centric, but now you're able to use Matlab in the GUI or in the notebooks on there, and even integrate it into your Python notebooks, which wasn't possible on the NRP before this project. And I believe there were previous attempts to integrate Matlab onto the NRP, but they kind of just fizzled out for one reason or another. So just briefly going over our data. The wearable device we get our data from is the Generation 2 Oura Ring. The Oura Ring uses, sorry. Sorry, I'm not sick, I promise. So the Oura Ring uses PPG sensors to measure heart rate variability, and respiration, a negative temperature coefficient sensor for skin temperature, and a 3D accelerometer for gauging activity levels. And we have Oura data for about 65,000 people for the year of 2020, and we have about 10 months of data at a 1-minute resolution. And for most kinds of modalities, we have the data available only when the person is sleeping, because during the day, they're up, they're moving, they're washing their hands and whatnot. So it's not quite as accurate during the day. But for some modalities, we have it 24/7, as long as they're wearing the ring, of course. So for skin temperature and activity, 24/7. And overall, the important thing here is that we have a lot of data from different modalities. So we need efficient data analysis and feature extraction methods so we can apply these without massive latencies. Yeah, this was supposed to be a GIF, but I'll just explain what's going on in a sec. Given that we work with longitudinal data, our lab is interested in time frequency analysis. So namely for this project, we were interested in Matlab, in integrating Matlab into our current JupyterLab workflows for fast and reliable time frequency analysis, in specifically the form of the continuous wavelet transform. And the reason you might use the CWT over, for example, a Fourier transform is because sometimes our signals are non-stationary, so changing in periodicities over time. And sudden changes in periodicity can be indicative of some interesting things, like, for example, sudden illness onset or some kind of a sudden environmental change. And the CWT is pretty good at capturing these abrupt changes. And what would be the skiff would be pretty good at showing what the CWT is doing here. So the signal would be that line in black, and the wavelet would be in red. And the wavelet is basically dragged across the signal and convoluted with it at each time point. And the value of the convolution would be shown on the right. But basically, the higher up it would be going means that the periodicity of the wavelet matches the periodicity of the signal, which means that that period or frequency is pretty well represented in your signal. And here's a quick example of the CWT in action for one of my projects. And this has to do with environmental effects on the activity of ants. And this is in collaboration with, of course, my PI, Ben, and Dr. Abhishek Dolai. And here I use it to characterize the activity of the Asian weaver ant under various environmental conditions. And the top plot applies the CWT to the number of entries per hour into the ant nest over the course of 15 days. Nothing crazy going on there, no rain. And we see a pretty prominent 24-hour band indicating a stable circadian rhythm of activity. So 24 hours stably cycling. And below, we have a different nest subjected to rainy conditions for the first 7 days. Compared to the next non-rainy 8 days, the 24-hour rhythm is more dampened, no pun intended, and kind of scattered. So we can see that activity patterns may be changed, shifted, masked, using the CWT as a method of time frequency analysis. So now that we've established some background on our infrastructure, data, and the CWT, let me get into our actual pipeline and first attempt at trying to apply the CWT to our large-scale physiological data using Python. Like I said before, we're on the NRP. We're using JupyterLab, primarily Python notebooks, for pretty much all of our lab-wide coding. And I'm using Dask for parallel computing of the CWT across individuals. And I'm using a often recommended CWT package, PyWavelets. And using this pipeline, we quickly found an issue with our results. We found some odd behavior going on at that 24-hour band, not necessarily for the ants, but like our actual data, physiological human data. So we found some weird behavior going on at that 24-hour band, which indicates that for some reason, skin temperature cyclicity was constantly being disrupted. And looking at the data, there's nothing that would indicate this being an issue. So we went on to troubleshooting what could be going wrong. So we decided to sanity check the PyWavelets package we were using and found that even a pure sine wave shown on the upper right with a period of 24 hours produces these weird wobbly results when you zoom into the 24-hour band on the bottom right, which isn't consistent with what you would expect from something with a, or just like a pure tone. And another issue with this package is that it doesn't seem to scale very well with Dask. So instead of processing like 100 people's data, 500, 1,000 at a time, I was only getting 30 or so before I would run into memory issues, which is not scalable at all. So we immediately dropped the PyWavelets package and moved on to a new one. This one is PyCWT, which is another popular CWT implementation with Python. And we found the results of our sanity check for this look as expected, and actually pretty close to what you would see using Matlab CWT implementation, although this particular package was somewhat slower than the first one, and did have similar issues with Dask. So just to recap, we've hit 3 issues so far with Python wavelets. One is the inconsistency between packages, which is a bit strange because most implementations claim to implement the CWT as described in a paper by Torrance and Campo, a practical guide to wavelet analysis. But as you've seen, they often come up with pretty different results. And this issue rolls into the second issue, which is none of us, meaning me and our lab, etc., are signal processing experts. So we may not be able to catch mistakes like this in Python implementations. And this is especially salient given a possible bug that I outlined on the last slide, a few slides ago. Lastly, the more correct Python implementation takes longer to run. And using Dask for the parallelization has not been working so well, as I've run into a lot of memory issues doing that. and trying to parallelize this for large data sets. So some level of memory abstraction from memory management would be desired, so the signal processing method can be more accessible to people in the lab without them having to constantly grapple with memory issues or learn how to toggle that. So we ideally want 1, reliable, well-vetted results, 2, some implementation fast enough that we can run the CWT on many individuals in real time, since storing these matrices, depending on the granularity, can cost upwards of 1 gigabyte per person per modality, and we have about 65,000 people in multiple modalities, so that's kind of expensive. And 3, we want something we can easily integrate into our existing Python workflows on the NRP. So I thought of using Matlab as a solution because I know that many people love it for its signal processing capabilities and its large-scale matrix operations, just for the speed, really, and the accuracy, because the code is well vetted by the engineers there. And provided that there's a way to get Matlab onto the NRP, it's not a very difficult language to learn, really. So the main question becomes, how do we get Matlab onto the NRP? So to make a long story short, we first needed a Matlab image for Docker, which was freely available on GitHub. Then we tried getting a network license file from the enterprise software licensing team at UCSD, which was kind of a pain, to be honest. And it ended up being like a confusing goose chase, but when we got it, it worked. And we had access to Matlab notebooks and the GUI and in JupyterLab, as shown on the right, some of the options. Though the network license was constrained to a single UCSD located server, meaning that if I wanted to launch a server with Matlab on it, I can only spin up from the server attached to that license file. And this kind of defeats the purpose of having this distributed computing network like the NRP, if you can only spin up from one server, really. And it's really a hassle if every institution or every single lab group needs to have their own unique license file. So that was a no-go, and that's when we reached out to Sumit et al. To chat about an NRP-compatible solution. And that's when we settled on the bring your own license approach, where individual users can just log into their MathWorks accounts on the NRP through their institution or personal MATLAB licenses. And they would have access to everything they would on their local machines, like MATLAB on the GUI, as you all know, and the integration with notebooks too, if you have that going on. And you can also get the computational benefits of the NRP, which is why we're so set on getting Matlab onto the NRP. So finding an elegant solution to this integration problem for a distributed network was a huge win that we owe to everyone on the MathWorks side of things, and specifically to call out our fantastic systems integration engineer, Dr. Dmitry Mishin. Okay, so the integration is really the first step. So we moved on to Matlab's implementation of the CWT from the wavelet toolbox. And it looks, as you would expect, much like the second Python package implementation. Now, how fast can it go? I ran on time the CWT for batches of samples from about 1 to 900 or 1000. And honestly, I think some lines kind of peter out just because I ran out of RAM. But to be consistent, I used the AMD EPYC 7502 32-core processor with 64 workers and 256 gigabytes of RAM total for all of these comparisons. I tried both the Python packages I previously mentioned with Dask, as well as a different multiprocessing package in Python called multiprocessing. And I compared these Python methods to the Matlab parallel pool of workers, which uses parallel computing toolbox. And on the right, you can immediately tell that I call out some memory management issues with Dask, where Dask is basically unhappy with having to manage the output of the CWT, which I mentioned can be about like up to a gigabyte per sample if you really crank up that granularity. And eventually Dask just kind of gives out. That's that red and that orange. So Dask ended up not being a great parallelization solution here. At least not one that needs minimal memory management. And in these benchmarks, Dask can be anywhere from about 10 to 100 times slower than the purple MATLAB power pool solution. And as for multiprocessing, though, it does quite well, much better than Dask. And it's not very difficult to learn to use. And worst case scenario, it takes about twice as long as the MATLAB solution to run. And we do see that the MATLAB power pool in purple is the fastest. And in my honest opinion, requires the least memory management, and overall is just the easiest to use. Here, I tried to speed things up a little bit using a GPU, the NVIDIA A10. And again, I kept with 256 gigabytes of RAM. I used MATLAB's GPU array functionality to run the CW code on the GPU. And I took the extra step of transferring the results from the GPU to the local workspace as just a regular array, not a GPU array or anything. And this isn't entirely necessary, as GPU arrays on MATLAB are pretty compatible with downstream operations, a lot of the functions. So this is kind of, it's not a necessary step at all. For us at least, because the transformations we want to do, for example, the max and min of the 24-hour band, things like that, it's perfectly compatible with MATLAB functions. And just keeping the GPU array and not transferring them to the local workspace would shave a little bit of time off of the MATLAB benchmark. And on the Python side of things, I use a Python package specifically for running the CWT on the GPU called PyTorch wavelets. And the runtime of this is pretty high, rather higher than the MATLAB. So I just kind of cut it off when I saw that, all right, it is consistently about 7x higher runtime than the MATLAB version. So using MATLAB power pool even would be preferable to using PyTorch wavelets, or even using CPU multiprocessing using Python would be preferable. So just to summarize, we were able to, maybe most importantly, integrate MATLAB onto the NRP for anyone who wants to use it, us happily included. And we've seen that MATLAB GPU arrays provided the fastest runtime of the CWT for large batches of samples. And importantly, we trust the implementation more than some of the Python ones. And now we have a few current use cases for the CWT in our lab. I've shown you an example of it applied to the activity levels of ants under rainy and non-rainy conditions. And I'm also using it to look at how extreme environmental conditions like, for example, wildfire pollution or heat waves impact biological rhythms. And we've also got individuals in the lab working on multimodal early COVID detection algorithms by feeding in the CWT surface, like the actual image, not the values, but just like the image, into a deep learning network for COVID prediction, as I said. And on the women's health side, we've been using the CWT to detect pregnancy onset and possible perturbations in biological rhythms that may be indicative of pregnancy complications. And that's pretty much it for me.